In this video, we are going to solve generalized Dirichlet integral. So we have this integral from 0 to infinity, sine of x to the power n over x to the power n dx. So the first thing we want to do is, we just replace x to the power n by y. That will simplify our integral a lot, which gives us y equals to x to the power n. If we substitute this, we will have y to the power 1 by n is equals to x, and differentiating both sides, n by n, y to the power 1 by n minus 1 dy will be equals to dx. Now we can use this. If we substitute x to the power n by y, our integral is something like this now. Integral in the change of limits, when x is 0, y is 0, when x is 0, x is infinity, y is infinity, and we have sine of y by y, and here in terms of d, in place of dx, we have 1 by n y to the power 1 by n minus y times dy. Okay, so now we can take this constant 1 by n out, and we have integral from 0 to infinity sine of y and y to the power 1 by n minus 1, and from this minus 1 dy. Now we see that we can use Ramanujan's master formula over here. What Ramanujan's master formula says is, let me I'm extremely sorry, this happens on my laptop. Okay, so now what Ramanujan's master formula says is this. If we have integral from 0 to infinity, and if we have t to the power x minus 1, and then if we have f of t dt, to integrate this function, this will be equals to gamma of x times phi function of this times phi function of minus x. Now you may wonder what phi function is. Okay, so phi function is we obtain this phi function in the following way. So if we would want to represent f of t in this notation, summation from n equals to 0 to infinity phi of n minus t to the power n over n factorial. If we represent f of t in this notation, and then while in this notation, what we have in pi of n, the thing that we require in pi of n will be actually the phi function, and which is used here. So this is Ramanujan's master formula, which we are going to use. Okay, so now if you aren't clear about what phi of n is, you will be clear in a moment when we do the example. So we have 1 by n integral from 0 to infinity sine of y to the power 1 by n minus 1 dy. So now we know from Ramanujan's formula that this is actually equals to gamma of 1 by n minus 1, and then phi function of minus x, that is 1 minus 1 by n. So now our main aim is to find the phi function. Okay, so for phi function, we should try to express sine y in this representation. Okay, so first of all, we know that Sine y is actually y minus y cube by 3 factorial plus y to the power 5 by 5 factorial minus y to the power 7 by 7 factorial, and so on. And the representation we want is the representation that we are seeking for the sine y is phi of n minus y to the power n by n factorial. So that looks like this: phi of 0 by 0 factorial minus pi of 1 y by 1 factorial plus phi of 2 y square by 2 factorial minus pi of 3 y cube by 3 factorial plus phi of 4 y to the power 4 by 4 factorial minus, and so on. So we basically are looking for this representation. Yeah, and for this we require phi of 0 to be, since we don't have the first term over here, it should be 0, and phi of 1 should be, since we just have y over here, it should be minus 1. Yeah, phi of 1 should be minus 1. Phi of 2 should be, since we don't have that term, it should be 0. Phi of 3, yeah, it's just 1. And phi of 4, it should be 0, we don't have that term. And phi of 5 would be, since we have minus, we don't have anything over here, so minus 1. And phi of 6 should be 0. So now we need a function that gives 0 for 0, minus 1 for 1, 0 for 2, 1 for 3, 4, 0 for 4, 5 for minus 1. It seems to be oscillating, so of course trigonometric functions might help. And if we just check, we get that phi of x should be minus of sine pi by 2x. If our phi of x is minus sine pi by 2x, we see that at 1 it's sine pi by 2 1, then minus 1, 2 it's 0, 3 it's 1, and so on. Yeah, it satisfies. So our phi of x is minus sine pi by 2x, and we can now substitute over there. Our answer would be but we have forgotten something. It's 1 by n as well, so we would have 1 by n over here as well. Yeah, now let's proceed. This will be equals to 1 by n gamma of 1 by n minus 1, and then phi of x was found to be minus of sine pi by 2x. Yeah, wasn't it? Minus of sine pi by 2x. So minus of sine pi by 2x should be there. So this phi of 1 minus 1 by n is there. That would be minus of sine of pi by 2, and in place of x we have 1 minus 1 by n. That would be 1 by n gamma of 1 by n minus 1, and then minus of sine, here we have pi by 2 minus pi by 2n. So pi by 2 minus something will change the trigonometric ratio to cos. We have minus 1 by n gamma of 1 by n minus 1, and then cos of pi by 2n. Okay, so this is our solution. And now if we want to check, we actually know a value for this integral. Yeah, you know that if n is equals to 1, integral from 0 to 2 sine x per n equals to 1, this is just a Dirichlet integral. that we all know, and its value is pi by 2. Yeah, so we can check with n equals to 1 in our answer to be sure if it works or not. If we substitute 1, n equals to 1, we get it to be equals to -1 times gamma of 1 by 1 minus 0. Yeah, we get it to be gamma of 0, and here when n equals to 1, this is cos pi by 2, that's 0. Now gamma of 0 is negative in complex negative infinity, let's say just infinity, and this is 0. So infinity times 0 is actually indeterminate. So we will be going through limits. Instead of 1, we would substitute a number that's really near to 1 but not 1. We substitute 1.001 minus 1 times cos of pi by 2 times 1.001. So now if I plug these values in my calculator, so -1 times gamma function of 1 by 1.001 minus 1 and cos of pi by 2 times 1.001. So I get this to be 1.5717 and 0301614. Okay, so you might recognize that this is actually pi by 2. Yeah, when if I try to find the value of pi by 2 from calculator, it will be pi by 2. If it gives me 1.5707. So we see that it's actually pi by 2 in the limit. So this works, and we have solved the generalized Dirichlet integral. I hope you enjoyed the solution, and you also learned something about Ramanujan's master theorem. Okay, thanks for watching. See you in the next video.